Right, so we want a new file now. This is to actually do the actual problem, the tapered plate with the hole in it. So from simulation, we went into sketch, new sketch. So we just drawing top view of the tapered plate. So we started an arbitrary line, and there's another line somewhere along here. Right, so the little yellow with the vertical line through it, next to the cursor there, it says this is a vertical line, and that's the constraint here. Right, so again, we could go line, we could make it a construction line, so by clicking that tick over there. Right, so we go to the midpoint, and we could connect it. Let's go straight across. Then we could dimension. So we could click dimension, we could make this 100. This one, distance between the two lines was 200. And from the end to the midpoint, well, it's 50 millimeters, that end was, right? So we go 25 and 25. And there's several different ways you could do this also, but right, and for the circle is somewhere in the middle here. Again, we could do our math dimension. It's 20 millimeters, and it is 100 millimeters from the end. Right, so now we just connect our lines. Right, so there we have our top view of the plate, exit sketch. Now we could go back to features and extrude. Right, we know it was 15 millimeters thickness. So there we have our plate. Right, so if it is you want to just make sure everything is correct in terms of our dimensions, we could go and evaluate over here. And you would see evaluation tools. Of course, we just want to measure, so we click on the measuring tape. And we know that the end was 50 millimeters, the shorter end, so we could just click on the line and we'll see 50 millimeters. The end on the back, the line on the back was 100, right? And we could see the red line, the distance was in fact 200. Diameter was 20 millimeters, which is what we had, and it was at the center is at 100 millimeters. Right, from the edge. Right, so the distance, center distance to the end was 100, which is at the middle, what we had. So this is one way of confirming our drawing before we proceed to the analysis portion. For the analysis, again, we went through this just now. If you're not seeing simulation, you click simulation up here and wait some time and you will see this tab come up here. Right, so we click on simulation, new study. Right, we will name it static, because it's a static analysis, static plate or whatever, right? And make sure static is selected over here, and then OK. And then we go to the same process. We have our materials. Right, so this is your custom material. Will remain here from the pre-analysis. Apply. Then we have the ends are fixed, so it's fixed geometry. Same procedure again. And then our loads. Right, so the load is on a line. Selected direction, we want it in the vertical, so we click a vertical line. Right, and the value of the force is 1000. Right, next step is our mesh. So what we will do our mesh study now. Right, so we'll go and create mesh, and we'll go down to a very coarse mesh. Right, so it's a very coarse mesh. And what we will do now, we will count, we will use this region around here and try and as a means of kind of seeing how our stresses are um, convergent. Right, so we have the coarse mesh. Right, so what we're gonna do, we're gonna keep remeshing this and keep getting finer and finer and see, do our mesh study. Right, so after we do a fine mesh, we click run, and this is our von Mises stresses. Right, so we could see that the maximum stress, of course, we expect it to be around the whole stress concentration. So you notice the stresses on the sides in terms of the maximum stress. Right? Um, if you want to have a look at the sigma x values, well, then we come on results again, define stress plots, and is in the x direction, so keep it at Newton per meter squared. So this is the stress in the x direction. So high regions of stress is in the back here, where it's fixed, and around the hole as expected. But if you want to get an idea of those high stress, you go and right click the stress, click probe. Again, select entity, so we click around the hole, update. So these are the stresses, the value of the stress around the hole. Alright, so it's hard to visualize these numbers here. Let's expand this. Alright, but you can see here the average, you could see the maximum, you could see the minimum. Alright, so the maximum stress is 78 megapascals. You can also click the little graph icon here, plot, and what that will do, that will actually plot now the distance as it goes around the hole, parametrically meaning that it starts at one end and going wrong. So this is from here to here is one loop around the circle, and you can see how the stress fluctuates. Alright, so again the maximum would be at the edge there, the 78 megapascals thereabouts. Now to do this mesh study, we could actually document this value here, 78 megapascals. Alright, so we plot the mesh, show, right click show, and we could do something simple. We could count how many elements are on here. So this is about 7 elements, and then we run the analysis, and again from this, but we just know that we document what is the maximum stress, and we keep doing that. Right, so we delete, unfortunately we have to delete it to do it over. We come on mesh, create mesh. Right, we want to override the mesh, so we increase the coarseness, the fineness of it. So we could come up to probably the middle here. Right, so we kind of increase the amount of elements. Again, we come here again, we run. Right, and then we do over the same results process. Define stress plot, change it to sigma x. Right, click probe, select the entities, click on the circle, update, and we can see the max here now is 81 megapascals. Right, again, so you can see now we have more points and the graph is beginning to look a little more smoother because we have more elements. And we could keep repeating this process. Alright, so I'll show you a result of what I did. Alright, so you keep repeating this process until you reach all the way up to fine. So you could stop here, do it again, stop here, do it again, stop here, all the way up to fine. Alright, so this here is just a small mesh study. So this is the number of elements around the hole, and this is the maximum that I had calculated, I had done when I was doing it. Alright, so I just roughly counted how many elements, and this is the value of the stress, the maximum stress. So it goes 77, 72. Right, so I plotted that stress versus number of elements around here. So this is what we call a mesh study. So you could see as the number of elements increasing, so this was sort of an anomaly here. Right, the value of stress would increase, but the difference in increase every time will get smaller. Right, so that is measured here by the convergence. So the convergence is really your new value minus your previous value divided by your previous value. So that is what convergence is. So we want to kind of put a percentage to how much it's changing every time we remesh. Right, so you can see it's 5%, 5%, and then it goes down to 3%. So I had maxed out how fine it was. So if it was capable of putting more elements, then it would have go down to maybe 2.8%, 2.5. So we reach a point where the line is just starting to slowly level off if it were to continue. So we can make a decision at this point and say, okay, um, at 17 elements around the hole, the convergence after that goes to 3%. So we could stick to this 5% here and let's use this figure here of 17 elements. So 17 elements is a good enough number of elements around the hole. If you go beyond that, then of course it will be even more precise or more closer to the actual value, but you'll be using more resources on the computer. Right, so the 17 elements is good enough. So that is how we would document this. We would show this plot in our report. Right, so coming back to our problem, well, we could say that this is the solution. This is our stress plot. This is our one minus stress, and it is below the yield strength, even the highest regions, even though we have the stress concentration. Right, we could look at the displacement. Displacement is 0.56 millimeters on the end here. And then of course is 0, where we fix, which is represented by 1 by 10 to the minus 30, which is 0. Right, so that is using the finite element analysis tool in Solidworks. And as we move on throughout the semester, we'll be using more advanced features. Right, so the task now is to see now how you could actually write up a report for this part using the pre-analysis, the types of elements used, etc. The results. Right, to get more information on your mesh, you could right-click your mesh, click mesh details, and you could see things like total number of elements, mesh quality. Right, so these are things that you could document for your report. Now, do not copy everything and paste it in a report. You need everything that in a report needs to have a purpose, and you must understand what it is you put in. So you will put down things like your element size, total number of elements. So those are um, good statements to put in terms of describing your mesh from SolidWorks. Right, mesh type is solid mesh. Um, you could see here also there's the mesh quality is high. Right, so as you're changing your mesh, these values are going to change. Right, so that concludes the activity for today.